So let's talk about how to compute integrals. By integrals here, we mean two different types of object. There are indefinite integrals and then there are definite integrals. Remember that indefinite integrals are families of functions, whereas definite integrals are just real numbers. They are equal to sine areas under curves. Now, well, for a given function v, the indefinite integral of v and the definite integrals of v are different types of objects. Their computations are actually quite similar. Both really boils down to finding an antiderivative of v. This is because if s is an antiderivative of v, then the indefinite integral of v is just s plus c, and the definite integral of v from a to b is just gonna be equal to sb minus sa by the second fundamental theorem of calculus. So you see that you can compute these integrals of v once you know an antiderivative of v. So what we're gonna talk about in these videos are the techniques for finding antiderivatives of a given function. Now, as taking antiderivatives is just the reverse process of taking derivatives, we can deduce rules for taking antiderivatives from rules for taking derivatives. The three main rules we use for taking derivatives are power rules, chain rule, and product rule. Their counterparts for taking antiderivatives are power rule, U substitution, and integration by parts. In this video, we're gonna start with the easiest rule, namely the power rule. If you already know what this is, why it's true, and how to use it, then feel free to skip to the next video. Just don't forget one subtle point, which is in this power rule, this exponent cannot be minus 1. Otherwise here, you'll be dividing by 0. Actually, do you know what the antiderivative of x to the minus 1 is? Note also that another way of writing x to the minus 1 is just 1 over x. So what's an antiderivative of 1 over x? Well, it turns out that an antiderivative of 1 over x is just the natural log. This is actually sometimes taken to be the definition of the natural log. We won't be talking about log yet in this video, but do keep in mind that this power rule here does not hold for r equals to minus 1. Alright, so now that those of you who know the power rule have left, let us discuss where this power rule for antiderivative comes from, and then we'll do some examples. Well, as we have said several times, this power rule comes from the power rule for taking derivatives, which I hope everyone remembers. Now, just by looking at this, some of you might already immediately see this rule. Then you can move on to the next video. But if you don't see it, and especially if you have trouble with abstraction, let's stay here and let us try to discover this together. First, let us do some practice to check your understanding. Tell me, what is the derivative of x cubed? Well, if you remember anything about differentiation, you know that this is just gonna be 3x squared. So that was a question about derivative. Now let's ask you a question about antiderivative. What is an antiderivative of 3x squared? Well, an antiderivative of 3x squared is just any function whose derivative is 3x squared, so an example would be x cubed. Okay, so now let's up the level a little bit. Can you now give me an antiderivative of x squared? That is, can you find for me a function whose derivative is actually equal to x squared? You might be tempted to reason that when you differentiate a power function, the exponent always goes down by 1. So if the derivative of whatever function this is has exponent 2, then this function must have exponent 3, so this must be x cubed. But that's obviously not right, because as you see, the derivative of x cubed is 3x squared. It's not x squared. So how can we modify x cubed so that its derivative is x squared instead of 3x squared? Well, some of you might be able to see immediately that the thing to do is to multiply x cubed with a third. Then when you differentiate this, you get 1/3 multiplied with the derivative of x cubed, which is 3x squared. And here 1/3 and 3 cancel. So the resulting derivative is just x squared, as we desired. Thus, an antiderivative of x squared is just x cubed over 3. Now, if you have trouble seeing this, don't worry. Then here's what you should do to build intuition. Do this exercise for me. Find for me the derivatives of all of these functions and see what you observe. Make sure to try this on your own first, right? And then come back here and we continue. Now, once you've tried it, you probably get something like this. Let's see if you have found out the pattern. Here, when you differentiate 2x cubed, you get 6x squared. When you differentiate 3x cubed, you get 9x squared. Differentiating 4x cubed gives you 12x squared. Differentiating 5x cubed gives you 15x squared. Then tell me, differentiating which function gives you 21x squared? Or in other words, what's the antiderivative of 21x squared? Or to make it even easier, I tell you that up to a constant, this must be of the form some number multiplied with x cubed. Could you tell me what this number is? If you stare very carefully at the pairs of number here, 2, 6, 3, 9, 4, 12, 5, 15, you will figure out that this must be 7. This must be exactly a third of this. And why is that? Why are these numbers here a third of these numbers here? Well, you probably already figured out for yourself. There's no magic here. This is simply because when you differentiate an expression like this, right, you keep the coefficient and you take the exponent 3 down. Thus, the coefficient in front of x squared in the derivative must always be 3 times the coefficient in front of x cubed in the antiderivative. In particular, if the coefficient of x squared in the derivative is 21, then the coefficient of x cubed in the antiderivative must be a third of that, which is 7. Once you've seen this, now you can easily find what the antiderivative of x squared is. Because here the coefficient of x squared is 1. So the coefficient of x cubed in the antiderivative must be a third of that, and thus must be 1/3. Some of you might get confused here because 1 is not divisible by 3, right? But we never said that these coefficients have to be round numbers, as you can see in these 2 examples here. To check if you understand, let us try one more. Give me an antiderivative of this. What number should I put here so that the derivative of this is 7x squared? Well, from our previous discussion, I hope that you can see that it must be 7 over 3. Alright, so now let us try to generalize this. Could you give me an antiderivative of x cubed instead? Again, you can't say x to the 4 because the derivative of that is 4x cubed. So to get just x cubed, you need to multiply this with 1 over 4. So you see, the antiderivative of x cubed is x to the 4 over 4. And as before, more generally, the antiderivative of ax cubed is just gonna be ax to the 4 over 4. That is, the coefficient of x to the 4 in the antiderivative is always gonna be a fourth of the coefficient of x cubed in the derivative. Now, if you continue this game, you can easily find that an antiderivative of x to the 4 is 1 over 5th x to the 5th. And an antiderivative of x to the 5 is 1 over 6 x to the 6th. And if you have infinite time, you can continue this with all natural numbers. But you don't, so let us just write a single general formula for this. Let's consider a general exponent n. Tell me, what would be an antiderivative of x to the n? Well, from the examples before, we see that this exponent here must be 1 bigger than n. So this exponent must be n plus 1. But as before, if we differentiate x to the n plus 1, we don't get x to the n, but we get x to the n multiplied with n plus 1. So to get just x to the n, we need to divide by 1 over n plus 1. Thus, an antiderivative of x to the n is x to the n plus 1 over n plus 1. Now, while we only look at examples where this exponent n was a natural number, this identity actually holds for n that are not natural numbers. It actually holds for all real numbers n as long as it's not equal to minus 1. For example, what is the indefinite integral of square root of x dx? What is an antiderivative of square root of x? Well, square root of x is really just x to the 1/2. So we can just apply the power rule for n equals to 1/2. Thus, the antiderivative of x to the 1/2 can be obtained by plugging in 1/2 into n here. And then you're welcome to simplify that expression for aesthetic reasons. Alright, so that's how we would find an antiderivative of power functions. Namely, we use these power rules which apply for all exponent n that are not equal to minus 1. Before we end, let us demonstrate how we can use this to compute indefinite integral and definite integral. Well, once you've found this antiderivative of square root of x, you get all other antiderivatives of this by adding a constant, so this indefinite integral is equal to this antiderivative plus c. Now, to find the definite integral, you want to use the fundamental theorem of calculus. Recall that if we call this antiderivative s, then the fundamental theorem of calculus said that this definite integral is just going to be equal to s of 1 minus s of 0. Another way of writing this is as follows. So you write the expression for s and then you put a little bar here with 1 and 0 here. This expression is by definition equal to s of 1 minus s of 0, i.e. to compute it, we would evaluate this expression at 1 and then subtract from it this expression evaluated at 0. This gives us the value of the definite integral. Alright, so that's all there is to the power rule. Up next, we're going to talk about U substitution.